Do you hear me?
Yes, Karel, we can hear you. Hi.
Okay. I think that it's slowly time to start. So some people are coming till now. Maybe that we will wait 2 minutes, 2 more minutes, and then we will start. Pavel, meantime, you can prepare again your questions.
Yes, yes, I already have prepared the questions, so I'm ready. Whenever you want.
We don't see you, huh? Karel?
Yeah. I don't know what is with camera. Seems that my camera is not working today.
Okay.
Okay. Pavel, put.
Yes, yes, I'm about
Hello, everyone.
Hello, Dima. Well, to the chat, I put the link for today's voting at Mentimeter. You can use either the link or the code on the top of the slide you see right now. So feel free to vote in order to have the information from all 4 EUXDAT webinar we have already had. Thank you.
Okay, it seems that today is voting lower number of people than normally.
Yeah, looks like. So should we move to the next question?
Yeah, I think that yes.
Yeah. Okay. So this is the next question, and the rest of the question will be at the end of our webinar. Okay, maybe we can pause our voting for right now, and we can start with.
Okay, so I will again start with a small introduction. So do you see my screen?
Yes, we do. Okay,
so it will be short, and then I will speak my colleagues. As I mentioned every time that we are trying to demonstrate how EUXDAT infrastructure and its pilot can support implementation of Green Deal, and also how they can support destination Earth and digital twins in Europe for agriculture and related topic, climate, biodiversity, and other. So as you probably who are here not first time, you see this first screen and other, because we have in Europe this Green Deal, but in Europe there is a Sustainable Development Goal. And now I promise to go to the biodiversity, and in the green color there is mentioned what probably is relevant or could be solved with the help of using EUXDAT platform with our analysis. There are some very ambitious goals in Europe, and to be possible to do this, we need to have some possibility how to make better knowledge management and how to take the decision based on the data. Here you can see some example of the data. Soon Dima will speak about this data and some improvement of this data during the EUXDAT project. You can see this is land use, and what we are trying is combine land use with other relevant data, and we work on the very complex model of land use, where you are able to integrate the different data which can lead to the assessment of biodiversity, about the protection of the soil and other. You can see here data from yield productivity, or there is possibility to combine this data with satellite images. We will speak about this later, and all these things was done using EUXDAT infrastructure. For the people who was not here, Pavel, if you can then later share to the chat the link to previous videos, because all these webinars are recorded, and you can go again to this presentation. On the first day, there were presented mainly this infrastructure, and also very detailed presentation how you can write parallel code. We had already also 2 pilot presentation, and now they will be the last presentation with 2 presenters, one from Plan for All and second from CERTH from the Greece. This is shortly from my side all, and I think Dima, now you can take the floor for your presentation. Dima, you didn't switch on your microphone.
Yeah. Sorry. So thank you for introduction, and well, I'm quite new to Zoom, so maybe it will take me some time to see where is the share button, because I don't see it.
It is down.
It's down. I see participants. Yeah, share screen. Okay.
Yeah.
So everyone sees the screen?
Yes.
Okay, so my name is Dimitri Kozhukh, and I work for EUXDAT, actually for pilot of open land use, and during the project we were developing further open land use data set, integrating some more data sources into it, changing a little bit the data model of open land use, and also because it was a project intended for application of information technologies into farming. We were searching for different data sources that could be also interesting for farmers. So the first idea, it was because it's quite easy in European Union. It's the program Copernicus running, and there is available digital elevation model for the whole Europe. So there were some ideas from the partners how to integrate digital elevation model into open land use, because then farmer can, for example, if he develops an informational system about his fields, he can select his fields, then he can generate various raster maps based on digital elevation model, for example, orientation of his field, or the slope of his field, or for example, topological wetness index, which means that it will show him in which area of his field it will be accumulation of water, and possible the farmer can think about some solutions how to drain this area or something such. So the first thing we integrated this geomorphological characteristics into open land use, and then after we were thinking about other data sets, and basically because there were too many of these data sets that could be integrated into open land use and that could be interested to farmers, we were extending basically and making more flexible the open land use model, so that in future everyone interested could integrate any information of his interest that is becoming increasingly available into the model. So I think that the webinar is maybe something more practical. So maybe let's take a look at what we have developed. It's all code. It's then will be shared through Jupyter notebooks after the project finishes, and you can basically read the documentation, try this code. The most important that you need to have Python installed, and there are some general libraries that I used, for example, NumPy or let's say GDAL. So it's not so much requirements. I think that everyone then can use the library we have developed for his own goals. Then I can maybe go through the code that shows some basic example. This example will demonstrate how to download fields from Czech land parcel identification system, and then the code will basically harmonize the land use classes of the fields into Hilux system that is basically proposed by Inspire directive, and then it will show the use of how to compute geomorphological characteristics for the fields. Then the beginning of the code is just the import of libraries that we need. Then it's some helping functions. It's just a couple, you know. It's usually these helping functions, it really relates to the data source you work for. For some data sources that are very standardized, for example, it's just a WFS service or just a shapefile. It will not have typically any helping functions because it's straightforward to work with these data sources with GDAL, but with some data sources you need to define some helping functions to facilitate some harmonization or to basically some manipulations, basic manipulations with the data. Then also part of the library is some functionality that is related to administrative units. It's very common that authorities, when they publish the data, they structure it by administrative units. So, for example, we take now administrative units in Czech Republic, and they are published by Czech Cadastre Office. And when you download, for example, parcels for the area, or if you even download LPs, it is structured by cadastral territories, and these cadastral territories is part of administrative units in Czech Republic. So here is just some simple functionality that helps to construct the graph of network X from the data about administrative units. So also sort of like helping functions. Then also it's import of requests library, which is basically if you download some data, it's useful to open request session, because, for example, if the connection breaks or the amount of data is massive, you want to set some options about these connections. Then if we go further, it's opportunity to save the data that you download to database backend. If you want, typically if you work with big amount of data, it's useful then to save it to a database. Then again, if you have really millions of records, it's useful to separate all data sources that you work for to different databases. Or let's say if you work as in this example, I will just demonstrate the data for one okres, which is sort of like district, which is not so big. Then we can just set one database for the data sources we will work with, and just set up connection to this. Then also it's very useful, like sometimes the metadata about the links for the data, as I have been speaking, it's divided by municipalities. So when you download the data, you need to know the code of municipality. And here is just some replacement dictionaries that you define in Python, which with important parameters. Some of it, it's, for example, last day of the month, because this concrete data set that I will download now, it's about the administrative units is Czech Republic, and it's basically updated each month. So here are just some parameters that is used in the URL link to download it, and because they updated each month, you need to basically to use the last day of the month as one of the parameter of this URL link. So here is just this, and then if you go next, it's basically some data structures that you could use in database when storing the data. Usually for most of the cases, I store it in a normal JSON structure, meaning that each feature has ID, then it has geometry, and it has properties, which is basically put in one field of type dictionary. Then it's defining this metadata with this parameter last day of the month, basically. Then because we have sort of like concept administrative unit in Czech Republic, and under it you have, for example, metadata and data source objects that is sort of part of it. So this I have object geoconcept, and it is the highest level object, and from which this object you can basically access metadata and data source. Basically, data source is a little bit higher than metadata on abstraction level, and it already have the files that you downloaded from the metadata that you have, and so on. So basically, here you create the geoconcept of administrative data source. Then you work with the parameterization. You change this last day of the month into URL address that you have in the metadata. And here you download the file. The file is quite big. So here, exactly in this live session, I just use method set data file, and I pointed to the local files that I already have downloaded. Then it's useful sometimes in this geoconcept of administrative unit of Czech Republic to make distinctions because they are on different levels, and so we defined sub-concept list, which is basically state. It's basically the information about the whole Czech Republic. Then you have basically the NUTS 3 level, NUTS 4 level, and then you have municipality and cadastral areas. Well, they all have similar data model. They have then the same data model basically as the concept of administrative unit in Czech Republic. So it's a level value, then parent, which is basically ID of the parent, and then these three attributes that I was speaking before: ID, date, and geometry. Then it's basically adding each because each sub-geoconcept, the files that I have downloaded, it has layers like ogre layers, and each basically layer it corresponds to this sub-geoconcept list. So basically, in this iteration, we add to basically this administrative unit in Czech Republic each of these sub-geoconcepts, and for each sub-geoconcepts we add exact layer from this downloaded file. Then we create this table in database. If I would do it really live, I would put replace, because replace means that if you have a table with the same name, delete it and create it new. And I use, because I already have this table in database, I use append, which means that check if there are some new features, and if there are some new features, append it to the table, and if not, just skip it. So this is what I do. Then it's just example that the name for the table is basically generated default from the name of geoconcept, which is administrative units in Czech Republic. Also, you can set while creation of table, you can select the scheme where you want it, and so on. Here is basically the part of code that shows the insert of the features from downloaded file into database. Here is basically these lines, they create a view for each sub-geoconcept. So for example, if you need just to select from the database information about municipalities, it creates basically this views in database. And if you want basically to select all municipalities, you would just type in database, select everything from municipalities. Then because the geometry type in this concrete case is point, then I use this helping functions that I showed in the beginning that basically downloads from WFS service the exact polygonal geometry of the features and replaces the point geometries that they were there originally. Then let's say here is an example of the of command that takes the sub-geoconcept of municipalities, and it reads features from this sub-geoconcept. One feature, just to show an example, it basically structured as I said, it has ID, data, geometry, level. So in this example, I just put municipality get data, and I get all data that is in that data set about the municipality. Here, let's say I create ogre geometry from this feature. Then I can use any ogre functions on this geometry. For example, here is I calculate the area of municipality using ogre function area. Then here is this helping function that creates the tree of this administrative units I was speaking in the beginning. Then also it's running because it creates the structure with all this 13,000 or like, sorry, 20,000 of different units in Czech Republic, and it by this attribute of level and parent ID. Then there is function, there is custom function that was there in the beginning because I don't want to demonstrate here some calculations for the whole Czech Republic. So I just select Okres Rokycany, which has ID 3408, and then I select all municipalities that lie in this district, because then I will download data of LPs just for these cadastral units. So here I get all cadastral units in this Okres Rokycany, here it's basically the same story with LPs. You define the basic metadata with parameterization, and you create this geo-concept LPs in Czech Republic. Because here it's not so many of computations for one aggressor, for one district, so I can show it live. I can use when I set up table option replace here, so it will be deleted and created again the table. Then here is the parameterization part where you select the most actual data from LPs, and here the sub-care concepts by cadastral units, and in table in a database, and you will have the structure where the data in each table, it will correspond to the data in a cadastral unit, and basically it will be parent table which will correspond to the LPs geo-concept that will have all these inherited child tables. Here it's basically adding these sub-geo-concepts, and here it's the part where for each sub-geo-concept, meaning for each cadastral area, it will be file downloaded and uploaded to database to corresponding table. And after it's uploaded, the data from the downloaded file, it will be removed. It's running. It's about 99 files to be downloaded and uploaded, but it's actually just takes maybe 1 minute to do all this. Anyhow, so in the next part, I show selecting just the data for one cadastral area, and here is because the point now is to transform the information about land use from this data source into HELOX. So here we define a dictionary that transforms categories of land use from LP system to HELOX system. It's just simple Python dictionary, the keys, the value in LPs, and the value of the keys, the value in HELOX. So here is this dictionary, and then it's interesting part which basically transforms the feature from the source to the OLU data set. So here you have basically, as I was saying, each feature has ID, geometry, and properties, and in this dictionary you have to define how you transform ID, how you transform geometry, because geometry, it also can have various transformations. It can have transformation of coordinate system. It can have transformations that in a way that it intersects with another geometry, and so on. But here I just show simple example without changing geometry. And then here is how you transform the properties. So basically you just take this dictionary that I was speaking before, transformation dictionary, and you create attribute HELOX value on the base of this transformation dictionary applied to attribute cultura ide, which is ID of the culture that is grown on the field. So here is just simple transformation, and here we convert next. We convert 10 features just to show to SQL insert statement that you can then just call one by one to insert data to database. So here is how it looks. I mean, you have like geometries, and you have this data information, which is just HELOX value transformed that I was speaking now, and you have ID, which is official ID of the land parcel according to Czech LP system. Then let's say it's example of create just one all the feature just to show you all these functions like methods like get data that they work and that you can create basically geometry from it that is Ogre geometry. Ogre, who doesn't know, it's part of GDAL. It's extensive library with everything possible, like calculation area of geometry, calculating different complicated intersections, and so on and so on. Okay, so now I have basically one feature selected, and for this feature, I want to calculate geomorphological characteristics. So it's then I need to do some special transformations because I will use the API that is provided by EUXDAT, and it gives the data about digital elevation model in European coordinate system layer 89, which has ID and EPSG system 3035. So just defining some basic transformation of this geometries, again using this GDAL library. Then for this API about digital elevation model, I need to provide the bounding box, which I'm interested in. Then the extent of the digital elevation model I want to get, and the out projection. Unfortunately, out projection, like output projection, just works this original coordinate reference system in which this digital elevation model is provided. So you can just actually use this value 3035, which corresponds to this European coordinate reference system. So then I get the requested digital elevation model. This is not a very like. And then I copy the digital elevation model to my home folder in Jupyter. Then I do the transformation of the field geometry into this coordinate reference system 3035, in which I have digital elevation model. Then I just, for example, create the feature, some cropping of the digital elevation model, and then I could export the digital elevation model of the feature to TIFF to work with it further in any desktop JS system. Then I can calculate slope of the field, azimuth of the field. Here is an example of this topological wetness index that is calculated for the field, and its visualization. It's also can be then exported in the same way to TIFF, and you can work with these features in JS. Any desktop JS, that also have some helping functions that calculate statistics. For example, here is topological wetness index statistics for this field, mean value, maximum value, minimum value. The same for digital elevation model, min, max. Again, like all this, it will be provided. Maybe what is interesting here, I don't know if it's really time for this, but you can define different transformational dictionaries, not such simple as I have shown, but also it can be some more complicated transformation dictionaries where you can, for example, take intersections of the geometries, or let's say you can take attributes and accumulate attributes of all intersections in the features. Like all this, it will be provided. So now maybe let's and it's all about like all this. It's about basically that we will provide this library, and also we will provide this transformation dictionaries and helping functions for all identified data source so that people can without problem download the data sets, maintain these data sets, do all the transformations that they need. And maybe it will be good if people will basically identify new data sources. Again, if people will basically write some harmonization dictionaries, so like helping functions to work with data sources and contribute it back to the library. So this is about open land use library, and now I would like to speak about automatic classification of the features. So it's basically automatic classification of land use, and the idea is such that you basically download images from Sentinel. You use at first a segmentation algorithm to segment the image into some logical segments, and after you train the model that will help to say to which land use class this segment falls based on the pixel value compositions. So here it's some I will share it. It's some code that because I trained the model for the whole Czech Republic. So at first I needed to find out the tiles of the sentinels that lie on the territory of Czech Republic. There were like 16 tiles, and then here is the function that for each tile for a summer period of 2020. For basically, I used the end of August 2020. It finds the image with the least cloud coverage, and it basically returns the tile and the product for this tile that has the least cloud coverage. So here it's just demonstration of, again, you import the libraries, then you define some helping functions. So here you have the tiles that is needed to cover the whole Czech Republic. Then we have ground truth data in this case, which is data from Czech cadastre. It's basically the center points of the parcels with its land use type. And then basically you take because I try to prototype on some computers that are not so powerful, so I need then to basically download to open each band separately. Then each band I divide also in 1000 by 1000 pixels, and I create segments from it. So maybe it will be interesting for you to see how these segments look like. So I just will show you in QGIS how it looks. So here is, for example, it's image 1000 by 1000 pixels. So here I at first use the function of sk image to select this image segments by superpixel algorithm, and then I use GDAL function polygonize to get basically polygons of these segments, and I need to polygonize because then I need to correspond to this data with the data about land use from cadastre, because I need to select the segments that I will work with. If the segment is too heterogeneous, meaning that I have like the function that tells me that more than 80% of the segment, let's say, it belongs to one land use type according to ground truth data. And if the segment is homogeneous, meaning that it has more than 80% of land use of one type, I collect it, and if it doesn't have more than 80% of one land use type, then I delete it from the data. So in this way, I collect the data about these segments, and I collect the data about the compositions of the pixels. For each segment, I create a histogram of 3 bands that I work with. It's band 2, 4, and 8 of Sentinel, and I create histogram. The bins of histogram have widths of 100, and then I have the composition of histogram for each segment. So in the end, I have basically a matrix with the histogram composition of the segments and the land use type of this segment. And I use the composition of the segment to train the model, and the land use class, it's like the output of this. Now, currently, we're testing different types of algorithms to train the model, logistic regression, neural networks, and the ones that will have the least error, we will use like finally to train the whole model and to do the whole classification on computer of HPC in Stuttgart. Just maybe to show some image here. So here I read basically because the values that I collect, I store them, and here it's for example some histogram showing 3 segments of let's say second band, and you have basically the green. It's not maybe the best visualization, but it's just to show that the segments that have the same land use classes, they have more similar histograms, and this is actually proved. For example, I have 6 segment which has land use type 14, 7 segments that has land use type 14, and then 8 segments that have land use class 7, which is like different. And then it's different metrics and distances to calculate the difference between histograms. So in this example, I use some Wasserstein metrics, which is not that any particular reason why I use it, just because it's already part of sklearn library. So I calculate Wasserstein distance between 6 and 7, 7 and 8, and 6 and 8, and we see that the histogram distance between the segments that fall in the same land use class, they are closer than the distance between segments that fall to different land use class. So this is basically where we stopped. I have created this prototype that collects the data, and now yesterday I was actually testing different algorithms, but it's not ready to be presented. It will be presented on the end of the project. So maybe this is it from my side. If you have some questions, you're welcome to ask.
Thanks, Dima. Are there any questions? It was nice demonstration how to use EUXDAT infrastructure. So if you have some question about the experiences, or if you would like ask something about open land use, please use this opportunity and ask Dima.
Like all this information, it will be shared on our pages, and also you're encouraged to try it by your own. And if you have some further questions, you can then mail me at Dimitri at Seznam.cz, but it is in this presentation, so you will get my email address to ask the questions.
Okay, Dima, thank you. And now who will speak? Dimitri, or who will speak from the CERTH team?
Yeah, Ioannis is going to present you.
Okay.
Yeah, hello.
Hi.
So I will share my screen to begin with my presentation. Okay, can you see my screen?
Yes, we see your screen.
Okay, thank you. Okay, so to begin, I'm going to present a crop monitoring pilot from the EUXDAT project. Our reason for trying to design a kind of service to provide the crop monitoring applications was to try to solve the problem of diseases in agricultural crops. We know that always diseases were a major problem for agricultural businesses, and they cause very heavy, costly side effects in the production and the yield and the quality of the product. To narrow that down a bit, we focused on stress based on diseases, meaning biotic factors. So we're talking about fungi, bacteria, and viruses, which it is known that they heavily impact the crops, and they also allow very short, a narrow reaction window for the growers in order to do any actions to prevent the worsening of the effects. More specifically, this pilot targets olive orchards, which is a very big part of the agricultural business in northern Greece. And it is also a product that is being exported a lot. Olive trees have many different pathogens that affect them. These are the most well-known of them and the ones that cause the heavier impacts. The biggest one is Dacus, and the other pathogens all are fungi and bacteria. And all these things result to major losses in the yield, because usually you have to apply some applications before you actually see the infection present in your field. And in case that you're not really quick for these applications, the result is usually lower yields and lower quality of the product. This affects both olives and olive oil. So what we wanted to use, what the components that we wanted to use in order to provide some kind of solution for this drive was, first of all, we accessed Sentinel-2 data using the FIS service from Sentinel Hub library. We computed some vegetation indices that allowed us to identify some parts of the fields of the vegetation that had some infection ongoing on them. And we built a model in order to be able to detect and classify parts of the field as stressed or not stressed, depending on the incidence of infections on them. The final target was to provide the classifications to the end users in an automated way. In order to achieve that, we used the Jupyter Lab part from the EUXDAT platform and machine learning libraries, which can also be used in the prototyping environment. I'll try to explain the way that we built our service for this part. Our test area was in Chalkidiki, which is one of the major olive production areas in northern Greece. And we had as far 2 years of sampling from the areas that you can see on the right. What we sampled was what in essence the sampling means. was that we went in the field and we designed some polygons, and we tried to assess the presence of any stress involved incidents for each polygon that we designed. We chose the area of the polygons relevant to the best resolution that Sentinel-2 data can offer, which is a 10-meter resolution. So we had a 20 by 20 meter surface in order to be able to include any offset of the sampling areas. And we applied an assessment that was in essence a percentage of the vegetation present in the sample and the vegetation that was covered by infection symptoms. We did some kind of differentiation between the drive of the pathogens. We differentiated between the pathogen Verticillium dahliae, which is a soil-borne fungus that actually creates some kind of water stress symptom. It can be correlated with water stress in the trees, which is the bottom picture. And Cycloconium, which is an airborne fungus that mostly impacts the leaves in the way that you can see on the upper picture. All the other categories that we tried to classify during the sampling procedure were all put together in a general stress factor class in order to be used afterwards in the analysis. So concerning the satellite data, we use Sentinel-2 level 2A data. Sentinel, as you know, is a constellation of 2 polar orbiting satellites. They have 12 bands. When we actually focus on 4 of them, which have the best resolution of 10 meters. And we have, you can have a new image each 5 days for the same region in most latitudes. So our data was accessed using WMS and FIS services requests from the EUXDAT platform, and we applied this for each sample that we had from the sampling procedure before. WMS, we know that it allows us to apply faster, you have faster acquisition for WMS. We need less storage room for this, and it actually enhances analysis for our datasets. And using the Sentinel Hub library and their FIS service, their feature info service, we can access directly the values in the pixels or the polygons that we provide, and not have to actually download the entire image or parts of the image. So this means that for anybody can just select the time range, provide some coordinates, and select even design some indices or any equations and computations you want to apply with the Sentinel bands, and directly get your results to a table and use it however you want. This is a list of the indices that we chose to compute. All these indices allow us to be able to detect any fluctuations in the health of plant tissue. And we used all of them in order to be able to select more correctly the samples that had any part of disease. So what we actually have here is index values and band values for each sample, and a specific percentage that correlates to the stress that we sampled on the field. We tried to be as precise as we could for the amount of vegetation surface that was relevant for each sample. Because in a given pixel, we do not have only the vegetation cover from trees, but unfortunately for us, we also have some ground or background vegetation included. but we managed to have some kind of answer for this by monitoring which percentage of each pixel was actually accounting for olive vegetation. And we used all these values, the index values and the band values from Sentinel, using a support vector machine model for classifying each sample into one of two possible categories. One that was stressed or not showing signs of stress. So we can see here that this is the previous version of the front end for this service. The user is able to design a polygon in order to represent any fields that he wants to apply these computations. And in the previous part, we just had the first part had only one index, the CRI2 index, carotenoid reflectance index, which is correlated to water stress. And you can have a specific classification for each pixel for this particular index. In this example, we can only have the values of the index, but in version 2, which unfortunately I cannot show you right now because it's under development, we have a very similar picture, but each pixel has a specific value of stress or not stressed. It's ready information for the end user. And you can also see the values of all the indices that are computed for each pixel inside the polygon. So what the end user can actually get from this is a map. So you can see all his polygons, which should be fields, whatever fields someone is interested in, with a stress incidence classification for each pixel. You can view via a pop-up window the vegetation index value and the classification result for each pixel without having to download the image. And in case someone is interested, he can download the GeoTIFF or WMS layer for the polygons that he has selected, or download the CSV file just with the tables of the index values and the classification. So what we, in essence, can have from all these this pilot is a model that can be used in order to provide the classifications of stressed or not stressed into a field or a pixel, and with quite sufficient accuracy. Of course, the accuracy that we can have from a service like this is lower than what could be achieved from using UAV or other sensors, and of course with better spatial resolutions. Although this, the positive thing is that we can cover very large areas and we can have a new image every 5 days, so the classifications can be done for many places and for very lower cost. What we could do to increase the accuracy was to, of course, retrain our model or provide more samples or check more what the incidence threshold could be. This one could also be a feature that would be on the choice of the user in order to select from which percentage and above someone would select to classify his field as having some kind of stress and further check for this particular method. And of course, validation methods play some role on the part of the machine learning training, but all these can be, you can actually try indefinitely and always provide more accurate results. So this was all from my part. Of course, for any questions, I'm open for you. Okay, so if there are no questions, maybe Karel? Can you hear me? I hope I was
Yes,
not
yeah,
muted.
yes, we hear you,
Okay, okay. I hope I was not muted for the entire presentation.
Maybe from my side, I have a question. For which time period you have collected the data from Sentinel?
This was correlated to the sampling procedures. It was for the May to July periods for 2019 and 2020 for all the olive fields in Chalkidiki, which were in our test area.
Mm-hmm.
So these are the dates on which we based the training of our model.
Mm-hmm. Ioannis, and can I ask if the index of the stress, if it's calculated in the same way for May and for June, for example, or July, or is it the same formula for independently from if it's May, June, or July?
That's a good question. Of course, when you have some, let's classify them as seasons, we're talking about time periods that are too far apart. Of course, it's different for the vegetation that we are able to see in the fields. So we use the same model for classifying for the period of April, May through June, because depending on the weather conditions, the olives are on the same development level, and of course, if we try to apply this model in let's say September or August or in the winter, it wouldn't provide some kind of reliable result because it's totally different view and for the trees.
Okay, thank you, Ioannis.
Thank you. So anything else, or should I stop sharing?
Yes, please, if I can ask you stop sharing. Because Karel is not here, probably because of bad internet connection. I would like to thank you all for the presentation of the pilots. And I would like to share my screen with further questions regarding the EUXDAT and some topics around it. So let me share the screen first, and I will send the link for the Mentimeter to the chat as well once I find it. Where is it? Yeah, there we go. In case you don't have the link, there is the link again. So I move to the next question, which is based on what you saw or what you have already got to know from the previous webinars. Do you think that the EUXDAT can help to implement Green Deal? Is the next question. And you can vote using the link I sent again to the chat, or you can use the code, which I don't know if you see because of the control panel I have on the top of the screen, but I hope you do. We had 3 voters at the beginning of the webinar, so I believe we can move on to the next question because we already have 3 voters for this question as well. Destination Europe is the next initiative where EUXDAT can help. If you think so, vote yes. If you don't, vote no, or you cannot decide whether it can implement or not. And there we go, we have 3 voters. And we can move on. In which priority of Green Deal, the priorities you can see here, the EUXDAT can be the most relevant one, while you can choose many options, not just one. And we have 4 right now. Thank you very much for joining us. And therefore, we can move on to the next question, which is pretty simple. Are you interested to test the EUXDAT infrastructure based on what you saw? Oh, 5 voters. Cool. Great. We are getting to the more complicated question a little bit. If you are interested in EUXDAT infrastructure, which is the purpose do you intend to use it? And again, you can choose multiple options. And shall we wait for the 5th one while we have, yes, there we go. Okay, thank you. And we are getting closer to the end. While we want to know if you see that EUXDAT is relevant for some priorities in the next Green Deal call, while in the next question, you will have an opportunity to choose from the list of Green Deal calls to be relevant for EUXDAT. So we have 5 voters already, and we can move to the question before the end. So you can move the slider for each area of interest independently. And we wait a little bit for the 5th voter, if there is the 5th one. Great. Thank you very much. And we are getting to the end of the voting, which is, are you or will you be interested in joining the consortium for the next Green Deal call?
No, okay, ale že to nemá žádný.
Sorry, I have apologized. My computer fell down, so I lost for some time connection.
It's okay, Karel. We just finished our voting, so you have returned in just the right time. So thank you, everybody, for voting. And I'm stop sharing right now the voting, and the floor is yours, Karel.
Okay, this was our last presentation of our achievements, what we done in during the EUXDAT. I would like to ask if somebody from our colleagues, Jorge or other, would like to tell also something on the end. Jorge, Walter, would you like to tell something on the end and give some comments to our work, because it is last time during the project when we are presenting officially what we done?
Yeah, Karel. I don't have any particular question or important remark. I think you have produced very nice webinars explaining all the main features of the platform, and it seems that participants are interested on it, and yeah, let's see where this leads us.
What we see also on previous webinars, that there is interest to test the technology, but also there is opinion that this infrastructure is good for further research. So I think that we will be able to put this into future research and to find the way how to bring together. So if anybody is interested to join us, please contact me, Jorge, or some other colleagues, and we will be happy to discuss with you what and how we can do in the future with EUXDAT, and how we can extend it, EUXDAT services after end of the project, because I think that this is something what really fit well now with the starting Green Deal, and that there is number of big experiences from all partners, and we will be able to continue after end of the project. Any other comments, questions, remarks?
Karel, it would be very interesting to disseminate this project in Sicilian rural areas and to involve Sicilian rural areas in the next project. Okay.
Okay, thanks. Some other? If not, I would like thanks to all presenter for presentation today. I am happy about what they prepare. This webinar again was recorded and will be available very soon on the web, so you will have chance eventually to see some things again about our webinar, our technology. All four webinars are recorded and are available, and if you see something interesting, please contact us and we can discuss what we can do in the future. I would like thanks also to all attendants to be with us. Some people join us for all webinars, so I hope that it was interesting for them, and I hope that it is not last time when we have chance to meet. It is probably last time with EUXDAT, but I hope that soon we will have chance to meet about some other topics. So goodbye and good luck.
Ciao.
Thank you, everybody.
Thank you.
Goodbye.
Thank you. Bye.
Bye. Thank you, everyone. Bye bye.
Ciao, ciao, Karel. Bye, bye.
Bye.